we speak about dust radioactive effects in the Mediterranean and Sahara regions by satellite LiDAR means. Just a few seconds.
Thanks a lot for inviting me here. So this talk is about dust relative effects in the Mediterranean and Saharan regions by satellite LiDAR means. And first of all, I would like to acknowledge my colleagues, Tony Landi and Paolo Bonassoni from CNR ISAC, James Campbell from Naval Research Laboratory, and Jasmina Papalardo from CNR EMAM. So this study investigate changes in aerosol radioactive effects onto highly urbanized regions across the Euro-Mediterranean basin. And this is done with respect a natural desert region as Sahara and over a decade through space-based LiDAR observation. So this research is based on the monthly average vertically resolved aerosol optical depth, atmospheric profiles, and those are collected along 1 by 1 degree horizontal grid, and data are obtained from Calliope, is the LiDAR on board of Calypso, NASA Calypso satellite. This because the Mediterranean region is one of the most responsible areas to climate change and is highly densely populated by 500 million people, and is 30 or around 30 countries in Africa, Asia, and Europe. Also, the Mediterranean Sea is also one of the world's busiest shipping route, and the region is very different levels of income and social development. And basically, so the aerosol emission in Benelux and in Po Valley are mostly also are of anthropogenic origin and are deteriorating their quality. So the European Union air pollution policy followed what is so-called a twin-track approach. So setting legal limits for concentration of air pollutants and establishing agreements and standards to reduce emission at source. So some of the examples, so there are some industrial emissions and the road vehicles and fuel domestic stoves. So those are three branches that are to tackle the problem of air quality. But besides air quality, also aerosol in the atmospheric column can locally warm or cool the atmosphere, because especially the shortwave solar radiation is modulating, and also the aerosol indirectly are influencing clouds and precipitation. So in fact, for the first direct effect, so the aerosol species differently interact with incoming shortwave solar radiation, and also at a lesser extent with the outgoing long wave radiation that is emitted by the Earth's surface. So, and mostly you have to distinguish in between the reflecting aerosol like sulfates or marine aerosol. So those kind of aerosol species are increasing the planetary albedo, and they're responsible for cooling the surface. While, for example, products from exhaust and combustion process like black carbon are instead absorbing the incoming solar shortwave radiation and then are warming the surrounding air. And dust aerosol layers are in the middle in between two different species of aerosol because they can either reflect the incoming shortwave radiation and also trap the outgoing long-wave radiation. And of course, these both effects can alter the regional atmospheric stability, vertical motion, and also affect large-scale circulation and regional hydrologic cycles. And then this causing a significant regional climate sensitivity. So this is the evolution over time of the PM10 into cities, so to big industrialized metropolitan regions, like this in Milan, in the Po Valley. So we can see, so this is on red here, you can see the limit, that is a threshold fixed by the European community. So we can see that during the past 5 years, we have a sort of decrease. And for Antwerp, that is in the Benelux, we have the same, so we observe the same sort of decrease. So those data are taken by the European Environment Agency in 2018. So those are the anthropogenic hotspots. So we can see in the north, so this is a very industrialized region, as well as the Po Valley. Then in contrast to those highly anthropogenic regions, we have the Sahara Desert, that is the largest, so in Chad, is the planet largest single source of desert dust. So is the largest natural source of natural aerosols. So if we are going to examine the long trend for temperature, so we can see here that since the 50s, we have, so the temperature anomaly is constant, is also towards negative values, but after the 80s, so when more, so industrialization was higher, stronger, there is an increase. So both into the anthropogenic and natural region. Of course, this is also because of the CO2 emission that are influencing all the three regions. But this is surface temperature. And this is an example of how the atmospheric profile changed in the Po Valley, for example, in from 2008 to 2015 in the three regions. So even is here is the task. This is why LiDAR is very important, because it can give an insight to the vertical dimensions of the aerosol. So we can see here that the DAOD, so if you had a sun photometer, it will be not possible to have such a difference because we have almost the same difference. But from this analysis, we see that the aerosol is changed a lot. So more towards, so there is a bump here. So there is a decrease at surface that is much better for air quality. And there is a bump, so maybe it is some transnational aerosol transport at around 1.5 kilometer. So the same situation is verified. So this is the extinction coefficient. So it's seen in the Benelux. So where in 2008 we had a much more aerosol load. So this is also a sharp decrease in 2015. And also we have at the surface, there is much less aerosol. While for Sahara is a natural source, what is expected, we have almost the same average over among the two years in 2008 and 2015. So EU policy, they were effective, so in doing some things, as you can see here, and the natural is staying constant. And after the analysis, so if we want to have a more detail of that, so this is the percentage of increase or decrease of per decade of the aerosol optical depth, and the bottom of atmosphere relativity flux in 2007, 2016, so in those 10 years. And this is calculated using the monthly means value for from Calypso and using the tail sand slope. So is this kind of statistical analysis is telling us if there is a really decrease or an increase during the examined period. So all these analyses can be found in Landi publication that it was published a few months ago. And what is possible to stress from this table is that during the analyzed decade, the AOD trend, and also, so consequently, the total atmospheric turbidity for the Po Valley and the Benelux is negative. So we have 3.4%, so negative 3.4% and negative 16.5%. And this is associated with an increase of the incoming solar radiation at surface under cloud-free conditions. So this is what you have plus 3.6% and 16.6%. So this is not reported to this table. And also because the solar radiation, so the more solar radiation is increasing, it is reaching the ground. As a consequence, there is a net warming effect on the surface air masses is likely. And instead, what we see, so there is an increase in Sahara. So there is an increase that is a completely different trend. So this because also the Po Valley and the Benelux are also characterized by important sources of black carbon, and it's well known that such type of particle absorb the incoming solar radiation, and also they are influencing the vertical heating rate close to the major emission sources. And this is another, so how we was doing the using the Kali applied or extinction profile from the different aerosol species to the radiative transfer model. So in this case, we are going to calculate and compute the heating rate and radiative effect at the top of the atmosphere and at surface. So this is so there is a version of this radiative transfer model also in online. So this is the NASA Langley website, and those are the different aerosol species that are taken into consideration for the different types of for 2008 and 2015. So we are going to do this difference among them. So we can see that mostly the polluted is labeled by Calypso algorithm, the polluted clean, so the polluted continental and smoke are important. So we can see always that there is a decrease with respect to the in 2015. And this is the aerosol radiative effect difference. So what we get, so we have a sensible difference. This is at surface. So we have an increase in incoming energy from a shortwave radiation that it's among, in the first 5 kilometers, among 4 watts per square meter and even 7 watts per square meter in the balance. While the difference in Sardas is much more, so it's 4 and 8 times so less. So going to wrap this up. So and our message also with this study, we finally give quantitative evidence that changes in direct radiative effect under cloud-free conditions are associated with anthropogenic aerosol emissions, and those are visible into highly urbanized Euro-Mediterranean areas, the Po Valley and the Southern Europe, and the Benelux in Central Europe. And also we compare our finding with those of a wild and remote region not affected by human activity, as the Sahara Desert. And this region is taken as a reference. And what we see that still in the desert, the air temperature at ground is rising, but this is because since 4 years ago, there is still an increase of CO2, and this is weirdness because the AOD is almost the same and the temperature at ground is constant, while in the Po Valley and in Benelux, we have again an increase in the air temperature at ground, but we have a decrease in aerosol optical depth. And these in percentage terms, so we have less anthropogenic aerosol, this contributed to have 3.6 shortwave radiation increase at surface in the Po Valley and 16.6 in Benelux. This is because the European Union policies are effectively reduce the anthropogenic aerosol. This is less anthropogenic aerosol. So still, air temperature at ground is increasing because there is two combined effect, more CO2 from the 80s, but also less aerosol that are reflecting the incoming shortwave solar radiation. And this is the 10-year Calypso analysis. And what we can say that the European emission reduction policy worked, but still there is a lot to do. And there is a net radiative effect also plus 3.8 per year. And also, but still we have also to relate to meteorological phenomena that should be investigated. So thanks a lot for your attention.
Thank you, Simone, for this interesting contribution. Are there questions from the room? Michael Rossi.
Interesting talk. Let me tease you a little bit. Are you suggesting to use the decrease in aerosol optical depth as a tool for geochemical or geoengineering of climate change?
That's a very nice question. Actually, these results are very dangerous because they are increasing that. So more pollution is better for to say this is an effect. Of course, we have to check if benefits outweigh problems, because more pollution is more related to other stuff. But of course, so this kind so this is what there is another work that was showing the same, that in the southeast United States there was so it was called a cool pool because there was a lot of aerosol that were blocking the incoming shortwave solar radiation. And then when they started to implement policies at government level, there was an increase in temperature. So so in the wrong hands, that could be dangerous. I don't know if I was answering, so I'm not sure what to answer, but so that's what we observed. And I'm not advocating to pollute more in order to decrease the incoming solar radiation.
Thank you, Simone. Are Are there any other question? From those that aren't, please, Simone, look at the chat room if you have some.
It's fine. So maybe we can move on to the last talk of the
Yes.
session. That it is evaluation of dust mobile reanalysis using LiDAR dust extinction. And this is will be presented by Michail Mytilinaios from CNR IMA.
Hello everybody, my name is Michail Mytilinaios and I am a research fellow at the Institute of Methodology for Environmental Analysis of the National Research Council of Italy. In this work, we present the evaluation of dust model reanalysis using dust extinction profiles retrieved by LiDAR observations. This study took place in the framework of DustClim project, whose aim was to provide dust climatological information by producing a regional dust reanalysis for the North Africa, Middle East and Europe region, while our main objective was to evaluate the quality and the reliability of this reanalysis, combining dust-related data from different measurement techniques. The dust reanalysis was produced by assimilating coarse dust optical depth retrievals obtained from satellite observations of MODIS instrument over dust source regions in the dust module of the Monarch atmospheric model. The dust products generated by the reanalysis cover a wide range of dust-related properties, both optical and physical, such as dust extinction coefficient profiles, dust optical depth, and dust PM10 mass concentration. Just to give you an idea about the climatological product of the Monarch reanalysis, in this figure are shown the monthly normal and the seasonal normal results of the simulated DOD, where it is clear that it is characterized by an annual cycle. DOD seasonal maximum values are found over most of the source and transport regions during summer and spring, while minimum monthly values are found from November to December. In general, we can say that the temporal and spatial distribution of the DOD is in good agreement with the meteorological conditions prevailing in these regions each season of the year, like for example, the seasonal variability of the intertropical convergence zone over Africa. The evaluation of the reanalysis was based on dust-related observations provided by datasets found to meet specific requirements based on the characteristics of the Monarch reanalysis. In particular, we used measurements from satellite missions and ground-based networks because they provide high-quality and harmonized systematic observations, while their dust-related retrievals have been already studied and validated in previous studies. Today, we present the evaluation of dust extinction coefficient profiles produced by Monarch reanalysis compared against LiDAR measurements provided by Early Network and LIVA's Pure Dust database, exploiting LiDAR's capability to provide dust extinction profiles. In fact, various aerosol characterization methods have been developed based on aerosol optical properties provided by LiDAR measurements. Here, a dust discrimination method has been applied to LiDAR backscatter profiles in order to decouple pure dust from the total aerosol profiles, using as a reference the values of the particle depolarization ratio. The dust extinction profiles were retrieved by using a LiDAR ratio value typical for pure dust conditions over the study regions. Then cloud screening was applied to each profile, while measurements with low signal to noise ratio were removed from the final dust profile. In case of EarlyNet, dust extinction profiles were produced from high quality and simultaneous particle backscatter and depolarization ratio measurements made over 11 stations across Europe for the period 2012 to 2016. Similarly, the pure dust product of the LIVAS database was retrieved in the same way from a satellite-based LiDAR observation made by Calypso mission, providing dust extinction profiles and columnar integrated values of dust optical depth. LIVA's main advantage is that covers the entire geographical domain of the monarchy analysis at a high spatial resolution. In order to quantify the evaluation results, we used the following statistic parameters: the mean bias and the root mean square bias of the model with respect to the observations, the correlation coefficient between the two quantities, and the mean absolute normalized bias of the model. The evaluation results are presented over two different temporal and spatial scales. The metrics were averaged in annual level and by season, and the results are provided in grid and in regional level. The monarch domain was divided in 10 subregions representing areas of different dust concentration levels, including regions which contain the main dust sources and regions which contain the main dust transport pathways. I have to mention here that prior to any comparison, the modeled and the observed dataset had to be spatially and temporally collocated. Considering the evaluation against LIVA's dataset, and in order to investigate how the reanalysis reproduces the structure of the dust profile, we used three parameters related to the vertical distribution of dust, namely the dust optical depth, the altitude of the center of mass of the dust layer, and the mean dust profile by subregion. The DOD values were obtained by integrating the dust extinction over the altitude. Monarch reproduces very well the spatial distribution of the DOD, simulating the dust emissions and the dust transport towards the Atlantic Ocean. However, there are differences in the DOD magnitude over the dust affected areas and especially over the Sahara Desert. In particular, Monarch overestimates DOD over the dust sources of Libya, Algeria and the Bodele Depression, while underestimates it over Sahel and the Gulf of Guinea. However, the normalized error is quite low and the correlation coefficient is very high over all the regions of interest. The altitude of the center of mass of the dust layer is defined by this equation. The evaluation results showed that Monarch captures very well the altitude of the dust layer over both dust emission and dust transport regions, revealing near zero bias and errors, as well as high correlation coefficient. However, over the mountainous areas of Turkey and Iran, the simulated center of mass exceeds 3 kilometers, leading to an overestimation higher than 800 meters. Very high overestimation can be found over Eastern Mediterranean as well. The mean regional profiles show a dust elevation up to 6 km for all the subregions apart from the remote ones. The Monarch and the Livas profiles are almost identical over the dust source regions of Western Africa and Middle East, and for altitudes over the PBL in the Mediterranean Sea and in Western Asia. On the other hand, the model overestimates the dust extinction coefficient up to 3 km in the northeastern Africa, whereas the comparison over the dust transport regions of tropical Atlantic and Arabian Sea showed a clear underestimation of the dust extinction coefficient along the entire profile. If we put together the profiles of the evaluation results of the different subregions, we can see that for the lower altitudes, Monarch overestimates the dust extinction coefficient over the source regions, which are represented by shades of brown, while underestimates it over the dust transport regions represented by shades of blue in this graph. Then between 2 and 6 kilometers, the mean bias is very low in all subregions, with moderate underestimation under 5 kilometers and insignificant underestimation over this level. The root mean square error profiles reveal greater deviations over dust source regions, decreasing with height, while similar fractional gross error profiles are obtained over the regions that are affected more by dust, where the error is kept lower than 100% up to 3 kilometers. Lastly, maximum correlation coefficient values can be found between 3 and 5 kilometers in all cases. The evaluation against EarlyNet was conducted in a regional scale, combining measurements from groups of stations in the Mediterranean Sea and in Northern Europe. The DoD scatter plots show a quite high correlation coefficient over Northern Europe, whereas Monarch overestimates the columnar integrated values over the Mediterranean Sea at most EarlyNet stations in this region. This is depicted also by the mean regional Monarch profile over the Mediterranean Sea, where a moderate underestimation between 1 and 3 kilometers is followed by a higher overestimation in higher altitudes. On the other hand, there is a significant underestimation over the station of Dusanbe, but these results are not representative due to very few dust extinction coefficient profiles available at this station during the period of the evaluation. Lastly, we evaluated how reanalysis reproduces the temporal evolution of the dust layer over a certain location using the EarlyNet 72 hours dataset, which provides continuous measurements for 3 consecutive days. This experiment was performed between 9 and 12 of July of 2012 by 11 EarlyNet stations in the Mediterranean area. For this study, we did the comparison over Granada station, which is located close to the dust sources of the Western Sahara Desert. The sequence of the simulated profiles shows that Monarch identifies the presence of the dust layer in terms of time and of altitude, but not in terms of magnitude. The comparison of the mean 72-hour profiles show a significant overestimation in the free troposphere, up to 7 km, while a minor underestimation in the PBL could be due to local dust emissions of anthropogenic origins, which enhance the early-net profile at lower levels. The scores of the model within the range of 1 and 5 kilometers, which is covered sufficiently by early-net observations, reveal large bias, error at about 100%, and the correlation coefficient does not exceed 0.7 at almost all the altitudes of interest. For the same case, we computed the center of mass and the DOD for each profile, obtaining a time series for each parameter. The center of mass comparison shows that the reanalysis fails to reproduce the temporal evolution of the center of mass, which according to the early-net measurements is subject to a daily cycle, giving a negative correlation coefficient. However, the normalized bias between the model and the observations is quite low because the mean bias is relatively low compared to the altitude of the center of mass, which is reported higher than 3 kilometers in most cases. On the contrary, the DOD comparison shows a high temporal correlation since the model identifies the periods of the higher and the lower DOD. However, the model overestimates the DOD constantly. To conclude, Monarch reanalysis reproduces very well the spatial distribution of the DOD with low error and a high correlation over most of the regions of interest, but overestimates it over all the main dust sources. Moreover, the model reproduces very well the dust profiles over the main dust sources, especially in the free troposphere, whereas underestimates the dust extinction coefficient over the dust transport regions. It also captures the horizontal distribution of the center of mass in the most dust-affected regions, but not its temporal variability over Granada. On the other hand, Monarch simulates the temporal evolution of the dust load in the atmosphere, even though overestimates it. Thank you very much for your attention.
Okay. Thanks a lot for the presentation. We are in perfect time, so 2 minutes left. So if for quick questions. So it's always difficult to get questions before the coffee break. So if there are not questions, I will close the session. And I would like again to thank all the speakers.
One moment, please.
Okay.
Simone, there is another presentation by Zahari Peshev. It is a poster presentation that is a short talk, 5 minutes. Okay, we will leave with this.
Sorry.
Okay, don't worry.
Because I thought it was posted.
Dear colleagues, in this study we present results of remote sensing observations of the troposphere over Sofia, Bulgaria, performed during episodes of Saharan dust transport over the region. The main objective of the work is to compare two events of Saharan dust load over Sofia, Bulgaria, during periods of minimum in winter and maximum in spring activity of dust transport to the region. by LiDAR characterization of the aerosol dust stratification and properties regarding effects on the local weather and troposphere in terms of seasonal specificity. On the upper part of this slide are shown maps indicating the location of the measurement site as well as a picture of the receiving part of the three-channel LiDAR system. LiDAR measurements were performed on 6th of February, Event 1, and 12th of April, Event 2, in 2021 with the two aerosol channels at 532 and 1064 nanometers of our neodymium YAG laser-based LiDAR. On the lower part of the slide are displayed color maps representing time series of range-directed LiDAR signals at 1064 nanometers, revealing the aerosol dust stratification and its temporal evolution in the two cases under consideration. The color map for 6th of February indicates an event of moderate increasing dust load intensity being in its initial stage. The registered dust layers are located both superimposed on the local atmospheric boundary layer and also separately above the ABL. The color map for 12th of April shows a dust layer of relatively high density mixed and superimposed with the local ABL erasing its upper boundary. On this slide are shown Saharan dust and air mass transport forecast data. The two upper diagrams display vertical profiles of the dust mass concentration above Sofia for the measurement days, available through the BSC/Dream8B model of the Barcelona Supercomputing Center, together with the forecast maps as insets for the total dust load over the Mediterranean basin and Europe provided by the Skiron model of the University of Athens. The two lower diagrams show backward trajectories ending above Sofia during the larger measurements by the high-speed model of the National Oceanic and Atmospheric Administration of the USA. According to the presented data, on 6th of February, the transport of dust is conditioned by a stable zone of high atmospheric pressure over the eastern Mediterranean, determining a specific circular motion and distribution of the dust field over large areas around it. Registered dust layers are the result of direct long-range transport from regions of Northwest Sahara. On 12th of April, the origin of desert aerosols is also from the northwestern regions of the Sahara. The dust transport is direct in the typical for the period northeastern direction. Here we presented vertical profiles of the aerosol dust optical and microphysical parameters. In the case of the event 1, in conformity with the discussed above dynamic LiDAR color maps, the height profiles of the aerosol backscatter coefficient at the two LiDAR wavelengths indicate a dust load of moderate intensity with well-separated dust layer at a height of about 4 kilometers. In the case of event 2, the vertical backscatter profiles show much higher densities of the aerosol dust layers confined in the lower part of the troposphere, which is typical of dust intrusions over the Balkans during the spring-summer season. The corresponding backscatter-related angstrom exponent profiles for both cases show mixing of desert aerosols with those from the local ABL, with dominance of the former, as well as the presence of dust fractions with sizes well above 1 micrometer, as within the mixing height range, so in the observed separated aloft dust layer. On this last slide, a list of summarized features and main conclusions based on the results obtained in the work is presented. The comparison of the two considered here dust events show typical for both seasons features and characteristics of the dust loads in terms of intensity, dust height distribution, and mixing with other aerosols, affecting significantly the local weather and both the structure and aerosol composition of the local troposphere.
Okay. So
yes, the session now. This is truly the last contribution. Before closing this session, thank you so much, Simone, for sharing it. Where I have a technical modification of the program because just 2 hours ago, two papers, two talks were withdrawn from the presenter. So the session will start at 11, but then there will be two cancelled presentations. So the contribution, the recorded contribution at 12 o'clock will be moved to 11:20. Sorry for this trouble, but it depends not on our decisions. Thank you.
So
enjoy your coffee. Ciao, Simone.
thanks a lot, and I hope to meet you